So in this question here is an elevator, and we are told that there's a teacher, 60 kilograms. Important to note that, 60 kilograms. An elevator, it's moving downward at a speed of a steady downward speed, so it's a constant velocity. So the constant velocity, F net equals ma, the acceleration is 0, so the net force is 0, the forces are balanced. At that point in time, approaches the ground and the floor, it slows uniformly and takes 2 seconds to come to a rest. So if we define this as the positive direction and this is the negative direction, then our acceleration is delta v over delta t, and our final velocity is 0 minus a negative 3 meters per second over 2 seconds is minus 1.5 meters per second squared. Now, we weren't asked to calculate that, but we just could see that's what the acceleration is doing. And the scale reads newtons. We use this as the gravitational field strength, and we're asked to draw two free body diagrams. The forces acting on the teacher during the constant velocity and slowing stages. So this should be relatively easy for us because we know at constant speed the forces were balanced. We already did that. And this one is the force of gravity, and this one is the force normal, and they are equal and opposite to each other. When it's slowing to a stop, we know the force of gravity, Newton's law of gravity, G(m)m over r squared. Nothing has changed, so the force of gravity is going to stay the same, and it will be the same size as it was previously, so I use the same hash marks. But the net acceleration is in this direction. It's slowing on the way down, so the speeding up is in the positive direction. The force causing this happen is upward, so this normal force must be larger to produce an overall acceleration in that direction. With the net force, of course, being like this. And I made a little bit of a goof there. That was a minus 3, so that's a plus. Positive 1.5 meters per second squared could be defined. Positive is upward. And so that's our F net. Moving to the next question, we want to determine the reading of the scale. Well, in the constant velocity stage, the reading of the scale, the normal, is the force of gravity or the weight. So Fg equals Fn equals the force on the scale equals mg. So that is 60 times 10 or 600 newtons. At the slowing stage. So again, our free body diagram, we know this is 600 newtons, and we have a larger force normal, like so. Newton's second law tells us that the net force is the sum of the forces. The net force is ma, the observed acceleration, and the sum of the forces in this case are Fn and Fg. And we are looking for the scale reading, which is the force normal. So force normal is ma minus Fg. The mass, 60. The acceleration, we determined was positive 1.5, minus the force of gravity, which is mg, 60 times a minus 10. So this gives us 90, and this gives us 690 newtons. And we should have noted, even if we weren't able to calculate it, that the scale should read heavy. And that's because it's slowing down. We picture the teacher wants to maintain his current velocity, but he's forced to slow down. So that means that the scale gets squished. He wants to keep moving, but the scale is going slower. So the scale gets squished. And that's A3.